Okay, hope this is an easy one. All right, we've got this wall, and we know the thickness, we know the K, we know the temperature on one side of the wall, and we know that there's convective heat transfer on this side, and we know that the temperature in the ambient air is 0 degrees C. So we're supposed to figure this out, calculate the Q and the temperature of the right-hand side of the wall. Well, we do know, presuming steady state. Okay, so really, you can't really do this problem if you're not in a steady state situation. So in a steady state situation, somehow this is an infinite source of thermal energy, and this side over here is an infinite sink. So we know the temperature gradient is going to be something like, it goes from here. The temperature gradient will drop from here, some straight line gradient. Wow, it keeps going to here, and we don't know. It's probably dropping additionally as it goes across some sort of boundary layer. What we don't know is what the relative resistances of these two right here. So how are we going to solve this? Well, a couple of things we do know. We know because of conservation of energy that the heat that is transferred in through the wall must be the same as the heat that is transferred through the boundary layer. We know, so our equation for that is that Q, this is watts per meter squared, equals negative K delta T delta X. Okay, let's see. Let's see if we can figure this out. We don't know what delta T is. And then we're not exactly sure if this is relevant. So I think what I'm going to do as I look at this problem is I'm going to treat this as a resistor, a circuit, a DC circuit resistor with a total delta T of 100 degrees C. Excuse me, 200 degrees C. So I'm going to pretend like it is something like this. There's an equivalent resistance, and this is 200 degrees C. The current is what we're looking for. It's unknown, and this resistance, there's some sort of equivalent resistance here that we can compute. So the equivalent resistance, the equivalent thermal resistance, if we model this as resistors in theory, series, here's one and here's one, conductive. So they have an equivalent resistance equal to the sum of those two resistors, the individual resistors. The convective one, I'm going to put, conductive one. I'll just go ahead and put the number in there. I think it's cursed. So it's this from this, R from K plus R from H. So it's equal to the length over the K value times the A plus the length, not the length, 1 over HA. So let's continue here. So we have their equivalent resistance equal to 0.5 meters over 2 watts per meter degree C. I'm going to pull the area out, 1 over area. It's the same area for both, if we consider one-dimensional conduction through this wall. Plus 1 over 3 watts per meter degree C. So the equivalent resistance is equal to, let's see, 5 over 20, which is 1/4. So 1/4 plus 1/3 is, what is those, are sevenths. 1/4 plus 1/3. 1 over A meters degree C over watts equals, so if we turn these into sevens, 3 plus 4. Is that right? 3 sevenths plus, no, sevenths. What am I doing? I'm tired. 12ths. Let's do 12ths. So 3 12ths and 4 12ths is 7 12ths. 1 over A meters degree C watts. So this is equal to our equivalent resistance. So we could get the Q. That's what we're wanting to calculate, the Q. So let's get the Q from here. So the Q, we know, they want the little q. I'm not sure if we can get the little q because we need to know the area, the cross-sectional area. So this q, though, we can get is equal to 1 over the resistance. Oh, I see. Times delta t. We know the total delta t is 200. So let's go ahead and plug some of these values in. This is 200 degrees C, and we know that Q dot is equal to 12 over 7 times the area. And what I'm doing is I'm plugging this value into the R here and inverting it. So I have watts per meter degree C times 200 degrees C. And what I'm noticing is something's wrong with my units. Here, I did something wrong with my units. So here is, I see, these units are wrong. 3 watts per meter squared. Meter squared here. And then here, there's meter squared. So this should be meter squared. Meter squared. Meter squared. So we bring this area over to this side and we get Q dot over A equals this little q, which is what we're looking for, times, it equals 12 times 200 divided by 7 watts per meter squared. And you can see that in doing this, I've canceled out degree C here. So we have watts per meter squared. So that's equal to, see, 12 times 224, 2,400 divided by 7 is what? 2,400 is a little over 300, 300 something. 2,400 divided by 343 watts. I used a calculator. Meters squared is the Q. Okay, now what is the temperature? So we now have Q, and we're looking for this temperature here. So we know, again, the total Q is the same Q that is transferred through here as the same that's transferred through here. So we can use this Q and say it's equal to negative K delta T delta X. And let's solve for delta T here. So 343 watts per meter squared times the delta X, which is just the thickness of this layer, times 0.5 meter. That's really a very thick layer. Divided by negative 2 watts per meter degree C equals delta X. Delta T, what am I saying? Delta T. So 343 times a half is 170 divided by 2 is about, what is that, 85? So we're looking at about 85. I'm just doing this sort of, I guess I should use a calculator. 85 oops. Divided by 2 equals, oh, it's 86, so 85. And now I'm going to deal with the units. It's late at night, so I'm a little bit tired. So meters, one of these meters, this meter goes with that one. We lose the watts, and then this degree C. It's divided by degree C, so that becomes degree C here equals delta T. Notice I've lost my negative sign. It really is negative 85, knowing that the temperature, this one is lower than that one, so it's negative 85 degrees less than 200. So I know that's equal to 200, T minus 200. So I know my temperature on the right side of this wall over here, my T is 200 minus 85, which is 115 degrees C.